Okay, I'm going to look at problem 6.32 at the end of the chapter. And this one is a heat engine, and it absorbs 25 megawatts from a 400-degree combustion chamber and rejects 15 megawatts to an atmosphere at 30 degrees C. Okay, so we need to find the actual and Carnot thermal efficiency of the engine, and how much power does the heat engine produce. Okay, so first part here is that this is our heat, the rate at which heat is coming into the heat engine. This is the temperature of our source. Here is our heat that's dumped to our sink, our low temperature sink, okay? Or at least the rate at which heat is dumped to our low temperature sink, okay? So we'll use that information to actually perform both of these calculations. And then the final one is finding the power. Okay, so 632. So we're going to look for the, this should actually be like a subscript. This is our thermal efficiency actual. Here's our other term, our Carnot efficiency, and the rate at which we're doing work, which is the power output, right? So we have the rate at which heat is coming in to the engine, and our high temperature source, the rate at which heat is being dumped to our low temperature sink. Okay. Here's the governing equations. Here's our actual thermal efficiency with the rate, using the rate equation. And here's our Carnot efficiency, which is of course our theoretical limit. And it's got, you have the low temperature sink divided by the high temperature source. 1 subtracted by that. And then the other part is we need to make a conversion for the temperature. Okay. So the first part is coming up with the actual, right? Well, the actual is just the rate at which you're doing work compared to the rate at which heat's coming into the system. And the rate I'm just using essentially this, didn't write it down, but here's our equation for work out is equal to the difference between these two, right? The rate at which heat's coming in subtracted by the rate at which heat is being dumped to the sink. And that's all divided by how much coming in. Okay, so it's just 25 megawatts minus 15 megawatts over 25 megawatts. So the actual is 0.4. Then the next thing we do is calculate the Carnot thermal efficiency, which is the theoretical limit. And this is just 1 minus the fraction, the low temperature over the high temperature in degrees Kelvin, or in Kelvin. And then it's just sticking that right in here. It's 303 divided by 673. So that comes out to be 1 minus 0.45 or 0.55. Okay. And in this case, you look at, oh, okay, the actual is less than the theoretical limit, so we're good. Okay. So this is a reasonable claim. Okay, then the last part is just find the rate at which work is being done. It's just the rate at which heat's coming in minus what's being dumped to the rate at which heat is being dumped to the sink. So it's 25 megawatts minus 15 megawatts is 10 megawatts. And that's essentially it for this particular problem.